SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be studying how we're going to modify the steady-state behavior of the system in the presence of disturbance. Here, first we're going to find the relationship between the error due to the disturbance and disturbance acting on the system. Then we'll have some relationship through which, if you choose suitably the controller gain, or if you add the integral part to the controller, how it is going to mitigate the external disturbance in the system. Then we'll have some example on aircraft control system and how we're gonna mitigate the external disturbance if you choose suitably the controller part. Then we'll conclude the lecture. In this lecture, we'll be discussing the effect of disturbance on the steady-state error. If you remember the closed loop system corresponding to WS, we had YS equal to GP of S, GC of S, 1 plus GP of S, GC of S, RS, and plus GP of S, 1 plus corresponding WS equal to 0, because we are not considering WS equal to WS in that for the time being, and GPS, GCS, MDS. This is the expression we had in the last lecture, and also we had the error expression for the error. Error we had RS minus YS, and the expression RS, we can substitute the expression of YS here, and GP of S, GC of S, 1 plus GP of S, GC of S, RS, minus GP of S, 1 plus GP of S, GC of S, MDS. And if you solve the first two terms, we'll have 1 plus GP of S, GC of S, RS, minus GP of S, 1 plus GP of S, GC of S, MDS. In the last lecture, we have discussed this part, the effect of reference signal on the steady-state error. Based on the type of the system, we have discussed how the steady-state error gets affected. In today's lecture, we'll be discussing the second part, the effect of disturbance on the steady-state error. For this, so we'll not consider the contribution of the reference signal. Here, we shall ignore the contribution of the reference signal R of S. Since we are dealing with a linear system, we can see the effect of individual reference signal or disturbance signal or noise on the system, and we can combine them together once we are done for the individual effects. So that's why we are going with one by one. Now, the controller, so our purpose here, E of S equal to minus GP of S 1 plus GP of S GC of S MDS. Let's define the kind of plant and control transfer function we'll be considering here. We can write the plant and controller transfer function in the following form. GP of S, we can write the plant transfer function, which is general form for any kind of system it is valid. So we can write KPL, some constant gain in the system, TA1 plant S plus 1 and TA2 plant S plus 1 dot dot TAMP S plus 1. And let's assume the open loop zero poles of this plant, we can write SNP. This is the number of open loop poles for this particular plant transfer function, and T B1 PS plus 1 T B2 PS plus 1 dot 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 TBN PS plus 1. This part is basically numerator, which yields the number of zeros, and the denominator, which gives the number of poles in the system. So from this transfer function, we can further write KPL divided by SNP, NPS, and DPS. So here, this is the gain, and SNP, this is basically gain in the plant transfer function. And SNP, S to the NP yields the number of poles on the system. And this is the numerator polynomial, which yields the number of zeros in the system. And DPS yields the number of poles in the system. So we can write in this structure. And also, let's write GC of S equal to AC TA1 CS plus 1. Here C denotes the controller, here in the above P denotes the plant, and TA2 CS plus 1 dot dot TAM CS plus 1, and we can write the poles configuration, we can write in this structure S to the power NC controller TB1 CS plus 1 TB2 CS plus 1 dot dot TBNC S plus 1. And we can write this expression also in the following form, similar to the plant transfer function. KC is NC, NCS, and DCS. So this is equation number 1, let me write, and this is equation number 2. Is it easy to see that if you, from this equation number 1 and 2, from equation 1 and 2, Okay, here if you place s equal to 0 for the equation number 1 in this expression, if you leave s to the np, then this term going to be 1, right? And similarly, if you put s equal to 0 here, this term going to be 1. So now we'll see this fact here. It is easy to see that KPL equal to limit s tends to 0 SNP GP of s, that is clear what I just told, and KC we can write limit s tends to 0 SNC GC of s. We will substitute equation number 1 and 2 in this equation. Let's denote this the star in star equation. Substituting equation 1 and 2 in equation star yields, we can write GPS divided by 1 plus GP of s GC of s equal to, can write, if you substitute for GPS, KPL SNP, then NPS DPS 1 plus KPL SNP NPS DPS and KC by NC NCS DCS. And if you further simplify this expression, we can get KPL as NC NPS DCS SNP plus NC DPS DCS plus KPL KC NPS plus NCS. Why you are writing this S to the NP-NC structure? Because if you remember in our earlier lecture we have discussed, due to the presence of integral term in the PID controller, we can ignore the disturbance effect in the system. This is in this direction we are moving here. How we can come up with the integral term into the system and how it is going to affect our distant error due to the disturbance. Now we can write, so if we are having this structure and if you substitute this expression in the equation number star, we can come up with the error, the steady state error we can write, let me define this equation number 3. So substitute equation number 3 in equation star, we can get ESS equal to limit s tends to 0 is ES. This is we get from the final value theorem. Now limit minus limit s tends to 0, we can write KPL NC NPS DCS SNP plus NC DPS DCS plus KPL KC NPS and NCS into MDS. The disturbance acting on the system. It is clear that to able to completely reject the constant disturbance, we must have NC should be greater than 1. So from this expression, it is clear to avoid the disturbance completely and to get ESS to 0, we must have NC should be greater than 1. Why? Because if it is NC here, if it is greater than 1 in this case, then S will be multiplied to the entire function. And if you put S equal to 0, then ESS goes to 0. So what is NC? NC actually, if you look, this is the open loop poles in the controller. Open loop poles in the controller. So that's why to reject completely the disturbance effect on the steady state error, we should have integrator in the controller. So let me write. Therefore, there must be an integrator 1 upon S in the controller, so to reject the effect of disturbance on the steady state error. This is very, very important takeaway from this discussion. Let us consider there is no integrator in the controller, for example. PD controller. If you see the PD controller, what is the structure? We have U of t equal to KPE plus KDE dot. And if you take the Laplace transform, US equal to Kp E of S plus Kd S E of S. There is no integrator in the PD controller, but if you have PID controller, we have integrator in the control law. Basically, here the structure is Kp E plus Kd E dot plus Ki 0 to E tau tau. So if you take the Laplace transform, there will be Ki upon S, so there will be integrator. But let's assume there is no integrator in the controller. Let's assume there is no integrator in the controller. It means NC equal to 0. If NC equal to 0, then let me write further. From this, what I said before, this NC, DC and NP, DP here, this NP, DP, NC, DC, for S equal to 0, those terms going to be 1, right? So let me write NP 0 equal to 1, NC 0 equal to 1, S equal to 0 if you substitute, and DC 0 equal to 1, and dP is 0 equal to 1. In this situation, if you assume there is no open loop poles on the Planck transfer function, then we can write ESS. So it means if you assume MP equal to 0 and NC equal to 0 in this equation, let me define this equation number 4. Equation 4. In equation 4, if you assume there is no NC and no NP, so there is no open loop poles in the controller as well as in the Planck transfer function, then we can write ESS equal to minus KPL MD divided by 1 plus KPL and KC. So this is the case when NC equal to 0 and NP equal to 0. So there is no poles, open loop poles in the system as well as in the controller. Again, if there is open loop pole in the Planck transfer function, which is NP, if it is greater than equal to 1 or more than 1 poles are there, then we can write ESS equal to, if it is NP is greater than 1 and NC equal to 0, so this term going to be 0, right? And this term already 1, this term already 1. So now we can write ESS, we can write minus MD divided by AC for when NP is greater than or equal to 1. This is how we can say how the integrator plays an important role in control system. If you add integrator in the controller, we can reject the disturbance effect in the system. So we have both two cases in the control transfer function. If there is no integrator exists in the system, then how the steady state error would be. So I can write here. So this is the case, if you notice very carefully this in this equation. So here we have assumed there is no controller. In the controller, there is no open loop faults in the control system, controller block. But due to the presence of the open loop holes in the Planck transfer function, still we can manage the steady state error. How? If you increase the KC gain, here if MD is a constant disturbance in the system, if we assume, then if we increase KC gain considerably high, we can manage steady state error. This is also possible. So let me write here one note. If there is no integrator in the controller, which is NC equal to 0, then there we must have to increase the controller gain to reduce the steady state error. This is very important takeaway from this part. Now we'll take an example how our system is going to behave. So we'll take the aircraft attitude control system, what you have done before. So let's example effect of disturbance on PD. PD means proportional derivative, aircraft attitude or orientation control system. Let's have the following block diagram. We are having summing point here, and we have reference input R of S, and we'll look the modified PD control attitude system. So it is KP is here, and we are having disturbance on the system MDS, which is, we can say, constant. We'll assume the constant disturbance acting on the system, and we have the plant, the modified plant transfer function 1 upon IS square plus KDS, and this is the output, and we can close the, so this is minus this positive, this is positive, this is positive. So this is the closed loop control system. And from this, let me define this figure 1, and we have to find the effect of disturbance MDS on the steady state error in the system. From figure 1, we can write the plant transfer function, we can write GP of S equal to 1 upon IS square plus KDS, or we can write 1 upon KDS. If we take common, then we can write 1 upon KDS plus 1. So we have written this expression, if you notice, the plant transfer function in the structure. In the structure we have written, in the structure. And the controller transfer function, the controller transfer function, we can write GC of S equal to KP. It is clear that there is no integrator in the controller, because here we can say NC equal to 0, since there is no controller, no integrator in the controller transfer function. However, here we have in the plant we have one integrator. However, in the plant transfer function, in the GP of S, we have one integrator. So we can write NP equal to 1. Therefore, the steady state error, can be obtained as ESS equal to minus MD by KC. This is very, very important. So this is what exactly we have done in the previous example. So previous methods. This is actually what we have done. So in this case, there will be steady state error. So now, if you are very, if you are, as a control engineer, if you are very accurate about how much cases should be increased so that steady state error can be minimized. And for example, if you have some value and if you want to maintain some steady state error in the system, for example, if you are given, if we are given a specification on the steady state error, so that such that steady state error, for example, should be less than E max steady state error, for example. So this is the, as an autopilot designer, you want to maintain this steady state error, and you don't want to more than that. This is the maximum value. So from this condition, then we can the proportional gain Kp must be chosen such that Kp should be less than Md divided by E max SS. So this is how we can come up with the condition how the Kp or the controller gain should be chosen so that it can fulfill the objective on steady state error. This is very, very important. How we can achieve your mission objective. If you want to maintain a desired attitude of the aircraft or position, whatever. So, and if you want to maintain some steady state error in the final stage, what are the conditions we have to follow? So this is how we can improve the performance of the controller. Let's stop it here. We'll continue for the next lecture. We'll have some examples. So for whatever we have done on this whole topic, we'll have some example and we'll see how we can design the controller. Thank you.